Hello, this is Jack Jackson. This video is going to be about introducing the idea of a definite integral. Now, I assume at this point that you have been studying calculus a little while and you've already looked at the other main branch of calculus, which is differential calculus, looking at the concept of a derivative. And now we're ready to move on to our next main branch of calculus, which is integral calculus, or looking at the definite integral. Now, both of these basic two fundamental concepts of derivative and the integral are based on the one and only underlying concept that goes through calculus, and that is the concept of a limit. So ultimately we'll see that the derivative and the definite integral are based on this concept by taking some pre-calculus ideas and applying the limit. And it turns out that the derivative and definite integral are actually closely related to each other in sort of an inverse way, which we'll make clear in the fundamental theorem of calculus, which we won't get to in this video, but we will in a later video. So we're going to begin our study of the definite integral somehow in a way that's somewhat similar to the way we just began our study of the derivative. So if you look back at the videos that I have on derivatives, you'll see that the first situation we investigated that led to the idea of a derivative was examining a table that gave time and distance ordered pairs values for a car with, we might consider it had a broken speedometer, and we wanted to try to approximate the instantaneous velocity, what the speedometer would read, of the car if it actually would work. So what we're going to look at here is similar to that. It's kind of the inverse problem. We're going to be given a table of values of times and velocities of the car going down a long stretch of, say, the interstate, and we're going to suppose that the speedometer and clock work fine, so we can record times and speeds, but we cannot record distances very easily because, let's say, the odometer and the distance markings on the highway don't exist, or they're broken. So there's no direct way to measure distance, and of course our goal is to answer the natural question, how far did the car travel for the entire trip covered by the information in the table. So suppose we have this table down here at the bottom. We're given two times, time t equals 1 and times t equals 5, and t is going to be the time in hours since noon on a particular day, and v is going to be velocity. T will be in hours and v will be in miles per hour. So basically at 1 o'clock we look at our speedometer and we see that we're going 51 miles per hour. And at 5 o'clock we look at our speedometer and see that we're going 83 miles per hour. And we want to estimate how far we traveled in that time period from t equals 1 to t equals 5. Now, actually, if this is all the information we're given, we don't have a clue of really what's going on here in terms of the actual distance traveled, really, because, of course, the car could be doing anything. It could have pulled over and stopped for most of that time. It could be going really fast or really slow throughout the time. So to make things a little bit simpler, let's assume that the car is actually speeding up the entire time. So it starts at time 1 at 51 miles per hour, and at time 5 o'clock it's made it up to 83 miles per hour, and it's accelerating the whole way. Now, of course, this is unrealistic, because in actuality, even if you were driving that full time and you didn't take any breaks, the car would be speeding up and slowing down as you went around curves, and you went around cars, and you got behind slower cars or past cars or whatever. And so that would not necessarily happen. But let's suppose that even if it could just speed up the entire time, it wouldn't take it 4 hours to go from 51 miles an hour to 83 miles per hour. Of course, I had a student one time tell me, I had that car, that it took it that long to speed up that much. But anyway, even though the situation is a little bit simplified and unrealistic in that situation, the basic situation definitely is realistic, and that we're talking about times elapsed and velocities, and from that we want to reconstruct or compute the distance traveled. So here's our first basic question. So notice that this table doesn't give us very much information. We only have speeds at the beginning and the end of the time period. So even just using this information, though, can we get some rough estimates on how far the car traveled from 1 o'clock to 5 o'clock on this day, and how will we go about doing it? You might want to actually pause the video for a second and think about that, and then come back. Okay, well, let's think about it a minute. First thing we might do is realize that we might be interested in looking at the units. Okay, and we will see that T is measured in hours, V is measured in miles per hour. So oftentimes analysis of the dimensional units, sometimes called dimensional analysis, can help lead to the appropriate relationship. And notice if you take miles per hour times hours, the hours cancel and you're left with miles. So it seems reasonable that if we could multiply a velocity by an elapsed time, then we would compute a distance. And of course that is exactly what happens. A velocity really is well, at least it's a limit of a delta distance, delta distance over delta time. You multiply that by a delta time, you get a delta distance. So actually this is going to be the elapsed change in time from the beginning of this trip to the end. If we go from t equals 1 to t equals 5, is 5 minus 1, or 4 hours, and that's a delta t. So now the question is, well, what velocity do I multiply by? I know if I take this 4 hours and multiply it by velocity, well, I mean, one thing, we have 2 or 3 choices here, but one choice is to suppose we use the 51 miles per hour, for example. Okay, well, what does this basically assume? This assumes that it basically stayed 51 miles per hour for the whole trip, and just right at the last minute zoomed up to 83 miles per hour. Okay, so if we assume it was basically 51 miles per hour the whole time, then what would our estimate be? Well, here's a good estimate right here. The distance could be something I'm going to call L1, which is the velocity at 1 times the change in time, so that's 51 miles per hour. We assume it stayed that for the full 4 hours. That gives us a total of 204 miles driven. Now, why did I call it L1? Well, if you look back at our table, if we look at our table and we think of this as an interval, the t values are like x values on a number line, and we put them in increasing order, then the 1 is on the left and the 5 is on the right of that number line. So the 1 is at the left end of our number line, and so we can use that as our t value, and then find the corresponding v value that goes with that. So the 51 miles per hour is at the left end of our time interval. So it's actually v of 1, where the 1 is at the left end. So we'll call that the left estimate. The sub 1 means we're thinking of that all as one large interval, and we're just using the left end of that interval. Now, is there another way we could have estimated this? Well, here we assumed it was 51 the whole time, except for right at the end it jumped up to 83. Well, we could do it the other way around, maybe a little more realistic, is it started at 51 here, but immediately accelerated up to 83 and stayed that. Maybe they got their cruise control on and left at 83 for the whole trip. Well, that would be what we might call a right estimate. So potentially it's going to be just as good. So how would we do that? Well, I'll call that estimate right 1, or R1. And what we're doing is taking the velocity at the right end, the velocity at 5, which was 83 miles per hour, multiply that by our elapsed time, or delta t, of 4 hours, for a total of 332 miles. Now, since we were told that the car actually sped up during the entire trip, what can we say about these two estimates? Well, notice if it's speeding up, slowing down, we don't really know for sure if these estimates are too small or too big. But if we know for sure it's speeding up the whole time, we know that L1 was too low, because we assumed it was 51 the whole time, 51 miles per hour, and of course it's not. It's sped up, so it's going to go a little farther than that. Similarly, we know the R1 estimate's too high because, well, we were assuming it was 83 miles per hour for the whole trip. It only ended there. It was always actually less than 83 miles per hour if it actually sped up the entire time. So we know the actual distance is somewhere between 204 miles and 332 miles. Okay, well, we've got an estimate. Our estimate, we've got two estimates, 204 miles, 332 miles. Both of those are, they're okay maybe, but that's also a pretty wide range there. Okay, how can we get a better estimate? Okay, using just the information we have, how can we get a better estimate than this? Well, hopefully you said, well, you could take the average of these two. And the thing to notice is, anytime that we have one estimate of something that is too low and the other one is too high, when you average them, you're going to get an estimate that's better than either one of the two original estimates, usually, typically better. And that will be true because the amount one is too high and the amount the other one is too low kind of cancel each other out a little bit when you average. Now, in this particular case, there's no reason to believe the left or the right estimate is any better than the other one, and so we'll just do a straight average of the two. That is, we'll add L1 plus R1 divided by 2. That's going to be an estimate we're going to call T1. I'll explain later why we choose the letter T. Okay, so what would that be in this case? That would be 204 miles plus 332 miles divided by 2. That's 536 miles divided by 2 is 268 miles. So far, what's our best estimate? And given the information we have, the best estimate we can come up with is 268 miles. And that's our best estimate, but we know for sure D is between 204 miles and 332 miles. Well, okay, that's fine and good, but that's not a very precise range. This range here is pretty wide. So what could we do to maybe make a little bit better estimate? Well, we're going to need something else. What are we going to need? Well, we're going to need more information. We need more data. In other words, check the speedometer once, more than once at the beginning and then once at the end of the trip. Okay, so suppose we had a little extra information. Suppose the speed at time 3, right there in the middle, is 63 miles per hour. And so this would be consistent with what I said before, that the speed is increasing the whole way. Well, how could I do a better estimate than we had before? Well, what we could do is break it down on each piece. So we could find estimates. Maybe we could do an L and an R and a T estimate on this part, and then maybe on this part, and add them together. Or maybe just do an L here and an L here, add those together for a total L estimate overall, and do a right estimate on this one and here, and add those together for a right, and then average those two for a T. So let's see if we can do that. So, in fact, why don't you do that now? After you get your answer, come back, go ahead and press pause now. Okay, let's see if you got this for an answer. So I'm going to call this L sub 2 because I'm thinking of this as two intervals. There's the interval from 1 to 3, and then there's the interval from 3 to 5. So if we start with our first interval, how much time elapsed? Well, 3 minus 1 is 2, so that's a 2-hour interval. And what are we going to assume? Well, if we're doing an L estimate, a left-handed estimate, we go to the left end of this endpoint, left endpoint of this interval, which is the 1, and find the Y value or V value that goes with that, 51, and we'll use that 51 miles per hour. But this time we're going to assume it stays that for the first 2 hours. That'll give us a total of 102 miles, which is how far we're estimating it traveled over that first 2-hour period. We do a similar thing for this next 2-hour period. From 5 minus 3 is 2, so that's still a delta T of 2 hours. And we're going to assume that it's at the left end of this endpoint that we have our velocity, which is 63 miles per hour. So if it stayed 63 miles per hour all the time for 2 hours, that would be a total of 126 miles. Add those two estimates together, and we get a total estimate of 228 miles. Do a right estimate in a similar manner. If you don't already have it, press pause and then come back when you have it. Well, a right estimate would be similar. We would take this. Notice that the speeds are 63 and 83 that we're going to be using. That's V of 3 and V of 5. Those are miles per hour. Still 2-hour time intervals. So this interval on the first one says 126 miles. That's what we estimate on the second one above. The last one we have estimated 126 miles, and the last interval down here we are estimating 166 miles. 2 times 63 is 126. 2 times 83 is 166. Add those together, that's 292 miles. We're going to call those L2 and R2, 2 because I'm thinking of breaking this up into two intervals, one from 1 to 3, and the second interval from 3 to 5. And of course I could approximate a T estimate, we'll call it T sub 2, by averaging L2 and R2. So that's 228 miles plus 292 miles over 2 works out to be 260 miles. So what's our best estimate so far? Well, our best estimate so far is the 260 miles. But since we know V is increasing, we know it's between the L and the R. So the L is too small and the R is too big since the velocity is increasing. So we know the true distance is between 228 miles and 292 miles. Still a pretty wide margin of error, but quite a bit less than what we had before. So if you remember from before, let's see, what do we have? We had, we had it between, there it is, 204 and 332 with an estimate of 268. And our 268 estimate has been replaced by 260, and now we know it's between 228 and 292 miles. We've narrowed it down a bit. What will we need to narrow it down even more? Well, we need more data. Suppose I have the following data. So here I've increased the data points quite a bit. How many data points do I have? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 data points, which is actually n minus, if n is 8 data intervals, you have n plus 1 data points, which is 9. So there's an interval 1, 2, 3, 4, 5, 6, 7, 8 pairs, like that, successive pairs, or 8 intervals. Okay, what's the width of these intervals? Well, I made it kind of convenient and that all the widths are the same. So all the widths are 1/2 if you look at that, of the intervals. In other words, the elapsed times are all 1/2 an hour, 0.5 hours. Okay, now how would we do an L or an R estimate here? This would be an L8 and an R8 because they have 8 intervals. Okay, let's have you go ahead and see if you can work this out yourself. Use your calculator if you want, and work these out using the data that's in the table. Notice it is consistent with my claim that the speed is increasing the entire time. And get an L, an R, and a T estimate of D using this data. Work it out and then come back when you're finished. Press pause now. Well, let's see. How would I do an L estimate? Well, on each interval I would go to the left side. So for this first interval, I would go to the left side, which is 51 for the V, and then multiply by delta T of 1/2. So 1/2 of 51 is 25.5 miles that we're estimating there on travel that first half hour. The next half hour from 1.5 to 2, that's 2 minus 1.5, or delta T is 0.5, and we use the left hand side to determine the velocity, which is 53.25. Half of that is 26.625 miles. Similarly, we go across here, all the way across, with the last interval here using the 77.25. Notice the only data, the data that we did not use for a left estimate was the 83. That didn't show up in this left estimate. So each of these is the estimated distance traveled using a left estimate on each interval. Add those up, that's 249.5 miles. Now, I want you to notice something, though. We could have probably saved ourselves a little bit of work because all these delta t's are the same. They're half an hour. I could have factored it out and just added up the coefficients, added up the 51, the 53.25, the 56, and so forth, up to 77.25, added those up, and then multiplied the whole thing by 0.5. I wouldn't have had the estimates on each interval, but I would have still gotten to the final estimate for the total a little bit, maybe a little bit easier. A little bit more easily, I should say. Okay, moving on, let's try the same thing for the right estimate. Well, here I did it using the factoring out version. So I was able to factor out that delta t since it was the same each time. The delta t was 0.5 hours. All of these were miles per hour, so I just factored out my units. And then I add up the velocities as we go through here. Remember, these are the velocities at the right end of each one. So the end of the right end of the first interval was 53.25. So we go to the right end there to get that one, get the velocity. Then go to the right end here and get 56 and so forth. So notice we did not use the 51 at the end. We will be using the 83 at the other end. Okay? And then add those up. That's 531 times a half is 265.5. Now once again, since we know it's increasing velocity, we know the right estimate is still going to be too big and the left estimate is still going to be too small. So we do know that it's somewhere between there, somewhere between 249.5 and 265.5. Now we've narrowed it down quite a bit more. We have a much better estimate of where we are, and much better bounds on where we are, on lower and upper bound. And our t estimate, I'll call it t sub 8, which is L8 plus R8 divided by 2, turned out to be 257.5 miles. And that, of all the things we've come up with so far, that is our best estimate. Now, what would we need to do to get an even better estimate? Well, we need to break it down into more and more intervals of smaller and smaller widths to get more and more data in our table. Wait a minute, what is this more and more business? Doesn't this sound familiar to us? Isn't this something we've talked about before? What is the fundamental idea of calculus? It's a limit, right? It's that limit idea. So what are we talking about? We're talking about finding a limit, right? What limit? So the limit as the number n of subintervals approaches infinity. And since we made them the same width during each step, the common width, delta t, of each subinterval will also approach 0. It's kind of important that both of those things are happening, that the number of intervals that we have is approaching infinity, and consequently the widths are happening to approach 0 at the same time. So if we do this, if we take this limit, then the L and the R and the T all approach the actual distance D. In our next video, we'll come back and see this exact example. We're going to look at it graphically about what we just did here numerically. Okay, we'll be looking at some of the same stuff, but looking at it in a visual manner.